All right, in this video, we're going to introduce our section on measures of position, or how you compare to others in a data set. So in this video, we're going to take a look at using z-scores to compare data values. So a z-score, also known as a standard score or standardized score, measures how many standard deviations a data value is from the mean. So z-scores are going to be something that come into play with normally distributed data in a future videos. But it's essentially how many standard deviations a particular value is away from the mean. So we talked about deviation from the mean, where we take our value, which in this case we're using x, and subtract the mean. And if we divide that result by the standard deviation, that tells us how many standard deviations away we are from the mean. So a positive z-score is going to indicate an above average value. So if your deviation's positive, your z-score is going to be positive, because dividing by the standard deviation can never be negative. So a positive z-score indicates an above average value. A negative z-score indicates a below average value. And a z-score of 0, which in between there, indicates an exact average value. This, of course, under the assumption that not all the data points are the same. So a visual interpretation of z-scores, a z-value of 0 is the mean, and then if we have a z-value of 1 for a particular data value, then that's one standard deviation to the right, or one standard deviation above our mean. A z-value of 2 is 2 standard deviations above the mean. And going the opposite direction, a z-value of -1 is 1 standard deviation below the mean. So looking at where each data value stands, at least in terms of the mean, based on whether the z-score is negative, positive, or 0. So our formula, once again, is our deviation from the mean, which is x minus the mean. So I'm just using the population parameters here, but it works the same for sample x minus x bar over s. It's the deviation from the mean divided by the standard deviation. So this result tells you how many standard deviations you are away from the mean. So what's nice about z-scores is they can compare two different data sets that use different scales of measurement. So it allows you to, in essence, level the playing field if you're looking at maybe two different types of tests and their results. If they're on different scales, just because you got a higher score on one test compared to the other, the scale might be different. So we're going to take a look at an example of that using SAT and ACT scores. So usual data values are going to have z-scores between -2 and +2. So more information on -2 and +2 as z-scores when we talk about normal distributions in a future video. So let's look at our first example. We have the mean SAT score, at least at the time of this writing, is 1,059. And I do believe this is back on the 1,600 point scale. So 800 reading and 800 math, or I don't know if they even call them that anymore. But a mean SAT score is 1,059. The standard deviation is 210. Meanwhile, the mean ACT score is 21 with a standard deviation of 5.4. So a student takes both tests, and on the SAT received a 1350, and on the ACT received a 29. On which test did the student score better? And in terms of scoring better relative to the other students taking that exact same test. So first of all, it wouldn't be fair to just compare the 1350 they got on the SAT with the 29 that they got on the ACT. Even though 1350 is much, much larger than 29, these are on two different scales. I believe the SAT is 400 to 1600, and the ACT goes up to 36. So in order to determine which test the student scored better on relative to other test takers, we're going to calculate the z-score of the SAT score that they got and the z-score of the ACT score that they got, and compare the two. So the z-score for SAT is their score is 1350 minus the mean is 1050 divided by the standard deviation for SAT is 210. And when you calculate this, you get 1.39. So this student scored about 1.39 standard deviations above the average, above the mean average on the SAT. So not bad. For the ACT, the student scored 29. The mean score is 21 and the standard deviation is 5.4. So the z-score for the ACT is 29 minus 21 divided by 5.4, which is 1.48. So on the ACT, the student scored about 1.48 standard deviations above the mean. So comparing the two, now we've leveled the playing field. Comparing the two z-scores, the student actually did relatively better compared to other test takers on the ACT. So that might be very beneficial to the student in terms of college acceptance and or scholarships. So, but yeah, that's what z-scores allow us to do, and that's about it for this video. Thanks for watching. I'll see you next time.